In this video, we're going to continue with our discussion of the dot product. And here we're going to talk about projections, in particular the scalar projection and the vector projection. So what are those? Let's draw a picture. Suppose we have this line here, which is a vector. And let's call that vector A. And then we have another vector here, which we will call B. And when we think about a projection, we think about a light shining down straight onto the vector A. And if that were the case, what would the shadow of B be onto A? Well, if we draw a line straight down, so that this gives us a right angle, then we say that this vector that starts at, let's turn this into red, that starts here and travels along A. Oops. There we go. So that red vector there, that is our projection of B onto A. So let's try to determine some information related to that vector. And again, you can think of it as kind of like the shadow of B onto A, but we call that our vector projection of B onto A. So the first thing I want to do is I want to talk about the scalar projection of B onto A. The scalar projection of B onto A is just the length of this vector. Haven't we called this vector V? And this right here is just the length of V. Okay, so it's the magnitude of V. So how do we calculate the magnitude of V? Well, this is a right triangle, so we just use our trigonometry that we know. So we have some angle here, theta, and cosine of theta is equal to adjacent over hypotenuse. So cosine of theta is equal to the magnitude of V divided by the magnitude of B. All right, so we get that cosine of theta is the magnitude of V divided by the magnitude of B. Or in other words, the magnitude of V is just equal to cosine of theta times the magnitude of B. But recall, cosine of theta is A dotted with B divided by the magnitude of A times the magnitude of B. And of course, our statement here is we have another multiplied times magnitude of B. Okay. So this formula, cosine of theta is equal to this, was in our previous video. And here, when we write this out, this tells us that the magnitude of V is, well, we can cross off the magnitude of B here because those two cancel each other. So the magnitude of V, this vector, is A dotted with B divided by the magnitude of A. And that is exactly this formula up here. So the component of B along A is the dot product of A and B divided by the magnitude of A. So, and again, what does that mean? That is just the length of the vector V here. So let's erase all of this stuff. I want to keep that picture up here. Slowly erase it. You know what? Let's just clear it all out. That was taking too long. So redraw the picture. And again, the larger vector here is A, this is B, and we're going to call this one V. Okay, so we just found the length of V. That was our first statement up here. So how do we find the actual vector V? Well, the vector V is the vector that points in the same direction as A, but has length, this thing that we already calculated. So how do we find a vector in the direction of A? Well, one vector in the direction of A is the unit vector A, the unit vector of A. And recall that our unit vector of A is equal to A divided by the magnitude of A. So that's how we calculate our unit vector in the direction of A. So what is the vector V then? We already found the size of V. So the vector V is just the magnitude of V times the unit vector in the direction of A. And what was the magnitude of V? Well, that was the component of B along A, right? That's what we calculated in the first part. So if we rewrite all of this stuff, we get that V, this vector V, is equal to A dot B divided by the magnitude of A times A over the magnitude of A. So in the denominator here, we get the magnitude of A squared, but the magnitude of A squared is just A dotted with A. That was in this previous video. So this is all equal to A dotted with B divided by A dotted with A, all times A, the vector A. And now notice that this is a regular multiplication. This last multiplication symbol is just normal multiplication. It's not a dot product. The thing on the left, that A dotted with B over A dotted with A, is a scalar, right? Recall that A dotted with B is a scalar value. A dotted with A is, again, a scalar value. So a scalar divided by a scalar is a scalar. So we get a scalar times the vector A here. And that is our vector V. which our notation for that is the projection of B along A. So now we've been able to calculate that. Let's do a quick example of that calculation in this. So let's find the projection of B along A. So that is exactly this formula right here. Given that A is 1, 2, 1, and B is 2, -3, -1. Well, let's do the dot product of A dotted with B. So A dotted with B is 1, 2, 1, dotted with 2, -3, -1. All right, 1 times 2 is 2. 2 times 3, -3 is -6. And then 1 times -1 is -1. So we get 2 minus 6 is -4, minus another 1 is -5. What is A dotted with A? So what is the magnitude of A squared? So that's 1, 2, 1 times 1, 2, 1 dotted with. And so we get 1 plus 4 plus 1. This is 6. So we get -5 over 6 times the vector A, which is 1, 2, 1, which is equal to -5/6, -10/6, -5/6. So either one of these forms of the answer you can write. And notice that's exactly what we have down here. Okay. I'm going to actually let you do the projection of A along B. So you do the same calculation, but you reverse what A and B were from that previous calculation. So I'll leave that up to y'all to do as extra practice. We're going to move down here and do one other quick example. So let's assume that capital F, the vector capital F, and the vector D are the force and displacement vectors in moving an object. The work done by this force is defined to be the product of the component of the force along D and the distance moved. Well, remember the component of the force along D is what we just calculated earlier, right, was that scalar projection. And that is the magnitude of F times the cosine of theta, where theta is the angle between the vectors F and the vector D. Okay, so we get this formula here, which ultimately is just reduces down to the vector F dotted with the vector D, the force vector dotted with the displacement vector. All right, so let's do our example. A force is given by a vector F, which is 3i plus 4j plus 2k, and moves a particle from point P 2, 1, 0 to point Q, which is 4, 1, 2. Find the work done. So what is our displacement vector? Well, D is the vector 4, 1, 2 minus the vector 2, 1, 0, right? So this is the vector from P to D. So another way to write that is we have a point D, point P, and a point D. We have that vector there. That is a quick line. Point P and a point Q. And the vector D, the displacement vector, is the vector from P to Q, which is the vector 4, 1, 2 minus 2, 1, 0, which is 2, 0, 2. So we have that displacement vector. And our formula for work says that we take our force vector and we dot that with the displacement vector. Our force vector is 3, 4, 2. And we want to take the dot product of that with 2, 0, 2. And we get 3 times 2 is 6. 4 times 0 is 0. 2 times 2 is 4. So we get 6 plus 4, which is 10. And so that is the work done in this particular example. And that ends our lesson on the dot product.